Okay, hi, I'm Mikhail, and I'm going to talk about the process of porting libc to RISC-V, 32 and 64-bit. Quick recap, what is the libc in LLVM? It's a libc in the project. It supports several architectures, x86, ARM, ARM64, and, sorry. And now RISC-V, 32 and 64. It also supports building for GPUs, AMD and NVIDIA. There's a great talk on it last year. And it's written in C++. What is RISC-V? It's an ISA, an open set architecture. It's not a chip like Core i7. It's not a part of IP like ARM Cortex-M. It's an ISA like x86, ARM, and PowerPC. And so motivation, why porting it to RISC-V? And there is no ulterior motive. I just wanted to learn more about the project, about the architecture, and I was looking for a project to contribute on LLVM, and libc was the perfect match. Coincidentally, there was a patch a month prior that was adding basic support for RISC-V on libc, and it was memory functions, some strings, C types, Syscalls, but a bunch of stuff were missing, like CRT, floating point environment, threads, long jump, side jump, and others. So how do you add a new architecture to libc? This is actually from the commit that enabled RISC-V. You basically have to change 3 files. The first one is this LLVM libc architecture CMake. It basically queries from the compilers the architecture name. So for instance, it's going to query RISC-V 64, and this is going to be used as a path to 2 other files, entry point and headers, where you can define the system headers and the functions. Right, so this is the commit that enabled the RISC-V 64. It's basically just querying the compiler, it passes it, and it finds the RISC-V 64, which is going to be used for the path. And this is what the entry point file looks like. It's just a list of the functions that are going to be enabled for the architecture. And the headers, it's similar. It's just a list of the headers that are going to be enabled for the architecture. And that's basically it. You have a basic support with just these 3 changes of the new architecture for libc. And after that, it's just a matter of adding functions, running tests, fixing bugs, and rinse and repeat. So what were the challenges of supporting RISC-V? Basically, hardware was not available for me when I started, so solution was to use for Emulator. So there was QEMU, Spike, there are others. I actually started with QEMU user, but it would fail in some weird ways. Sometimes we would expect the syscalls would fail or succeed, and it would just happen the other way around. So for instance, this is POSIX EMA-device, a way to advise the system about the memory usage. And it returns 0 on success, but if you pass an invalid address, the first argument, it should return the no memory error, 12. And as you can see in the example, I'm passing new pointer, and it's just returning success, and we expect it to fail. So the solution for that is using QEMU system. For RV64 is easy. There are a bunch of images available everywhere. I think I started to use Ubuntu, so it just works. For RV32, you need to build the image yourself. There are options with buildhood or Yocto. I used Yocto because I wanted that my image had the compilers in it, so Clang and GCC, so I can test stuff inside the QEMU. And I couldn't find a way to do that with buildroot. And the only limitations that the images that are generated, they are limited to 1 GB of RAM. I don't know why. I tried to find out the reason, but I couldn't. But it is enough for testing libc. Another challenge, I think the biggest challenge, is syscalls. So RISC-V doesn't have backward compatibility with some old syscalls. They just don't offer them. So you have to update your code, a bunch of if and ifs to support these new syscalls. Some are simple, like open, unlink. They just change the name to open add, unlink add. Especially for RV32, they just add a suffix 64 or time 64. And some other cases just get rid of a bunch of syscalls and use just one. In the case of wait BID, wait 3, wait 4, you just have wait ID. And I'm going to show you some of the patches I said. I don't expect you to really understand the code, but it should be simple. So from easiest to hardest to more difficult. So FCNTL is just a matter of changing the syscall, and the arguments are the same. You don't have to worry about it. It just works. Another case is like dupe. So you have dupe and dupe 3. The number is usually the number of arguments that syscall takes. So if you want to implement dupe 2 with dupe 3, you just need an extra argument to the call, and you just set it to 0. It's going to be ignored, and it will behave like the dupe 2. Some other cases, so this is for RV32. If you look in the last green line there, so for LSIG in RV32, the offset of a file is 64-bit long, so you just have to split it into 2 arguments. So you just pass offset 64, the high bits first, and then the low bits then, and it will work like LSIG. Some other ones, you need to actually change the arguments. So for this schedule RR get interval, you need to pass this kernel time spec struct to the syscall. The kernel is going to fill it for you, and you just have to set back to the arguments from the call, the initial call. A little bit more complicated. And then you have the wait ID. So as I said, you don't have wait PID, wait 3 and 4. So you have just wait ID, and you have to handle all the different arguments, the return values. And so each syscall will work as expected. And that's the code for all of them, using just wait ID. Some other weird stuff is that in some architectures, some structs, they have swapped members. So in this case, it's struct siginf t. So you can see the error number and code, they are swapped. And actually, because the different arguments you're having to pass, the x86 was using the MIPS format, but we were not checking it. So it was a fun way it was fun to debug this. The kernel was just filling random stuff. I couldn't figure out. It took me a while just to find out that the members were just swapped. Some other small issues. Some syscalls cannot fail with the new syscalls that RISC-V offers. So some tests just need to be disabled, like epoch create. Another nice one was rand. So internally, we are using the Shor shift 64 star as a pseudo random number generator, but it was not random enough if you run it on 32, so we had to use another algorithm for the RV32. A lot of implicit conversions because of size, long, and stuff. In this example, we have a size of being assigned to size C. When warning error was enabled on libc, a lot of code was broken on 32, but at least we got to explicit set the conversions there. And RV32 has 128 long double, but no 128 integer. You can force the compiler to offer the 128 integer, but we have infrastructure there to avoid that. So we had a bunch of test cases that were just broken on RV32 because it's missing feature. But RV32, libc has the infrastructure to work around that. So yeah. So final slides. How is the support today? So today we have 946 functions in libc, and we support 86% of them. Zooming into what is missing, there are 30% that were added a few weeks ago. I still didn't have time to go there and check, but I don't want to jinx it. But it should just work. But the biggest issue right now is float 16. There is an issue I found a couple of months ago. I still haven't fixed it. That we cannot enable conversion from long double to float 16 on RISC-V. It's just not working. I opened an issue there. I do have a patch for it, but Unfortunately, it has a small problem that it breaks x86 backend, so I'm going to have a hard time landing there. And that's it. Thank you very much.